Okay, so we're moving on to chapter 4.5, which is electromagnetic effects. And as the name suggests, and we have, been introduced to electromagnets, right?
Yeah.
So an electric current can cause a metal to become a magnet. But what we're more interested over here is the fields, right? So an electric field, like basically, right, magnets, sorry, not electromagnets, electromagnetic effects. And so unit 4, chapter 4.5.1 is electromagnetic induction. So there are two things to keep in mind over here. One, as you know, electricity can cause magnetism in metals, right? Magnets can cause electricity in conductors, right? And when electricity is causing magnetism, right, it's going to have a magnetic field, right? Magnets causing electricity, and electricity itself has a magnetic field around it, right? So any conductor, a wire that is carrying electricity is going to, if you place a compass near it, you will see a deflection in the needle, right? The needle is going to point one way, or right, so in the north or whatever, and so it's going to follow the field of, like, the magnetic field that is being generated around the wire, or whatever the conductor is, wires mostly. So what we're going to talk about over here is, right, both cases. One, we're going to talk about like right, how, right, simply moving a wire that is not conducting electricity on its own, right? And for this, I'll actually take you to the book. I guess it's better illustrated, and then I'll give you the verbal explanation. Right, so where's the book? There it is. Right, can you see that?
Yes.
Now I don't know if we'll be able to reach the part today, or we'll have to wait for the next session, but right, there are a couple of rules to keep in mind, and they can be confusing, right? And you'll have to be using your right and left hands in a variety of contorted ways to figure stuff out, right? So when you get to the
Yeah.
part, I will be using my camera, right, to show you how to do that, hopefully. Okay,
Okay.
so over here we're talking about electromagnetic induction. It was discovered in 1831 by a scientist called Faraday. And so over here they've got this C-shaped magnet, right, in the blue, the North Pole and the South Pole. And the arrows over here are showing the different directions in which the wire can be moved, right? So it can be moved backwards and forwards. It can be moved towards either of the poles, right? And it can be moved up and down. So what they notice is, right, this wire itself it's just a wire, right? There's no electricity running through it, but it is connected to a meter. And what they notice is when they move the wire up and down, right? So we know about magnetic fields. You've done that, remember?
Yeah.
right? So there's a magnetic field going from north to south over here, right? And in this case, it's going to be a straight line. So it's similar to the arrow 3 and 4, right? I mean the line, right? So they're going straight. And so what happens is, right, in movement back and forth, so those are arrows 5 and 6, the wire is not cutting through the field line. Similarly, in arrow direction 3 and 4, it's moving along the field line. But in arrow direction 1 and 2, right, it's cutting. So it's moving perpendicular, it's cutting across the field line. Can you visualize that?
Yes.
Okay. So when the wire cuts through the magnetic field line, there's a slight deflection noted. Means what? Right? This device is there to measure current, right? And so a current is not like you're not passing current through this. Then why is there a current? And so they find, okay, fine. So if a conductor cuts through a magnetic field, it's going to generate a current. Okay, so that
Yeah.
was, and the current is going to switch. So if they move it upwards, which is in the direction of arrow 1, the deflection is going to be in one direction. If they move it downwards in the direction of arrow number 2, the deflection is going to be in the other direction. So the current is going to flow in the opposite direction.
Yeah.
And remember we talked about AC circuits, like AC, which is alternating current, where the direction of the current changes.
Yeah.
Remember that? And so this concept is going to be used in AC generators and AC motors and stuff, right? Where the current is going to switch directions, right? So,
Yes.
right, the direction in which the wire is moving across, cutting through the magnetic field is going to cause the deflection, and going back is going to cause deflection in the other direction, because the flow of the current reverses. The direction of the flow reverses. Okay. So this is one experiment, right? A straight wire and a U-shaped magnet, or C-shaped, whatever you want to call this. The next is a bar magnet and a coil, right? So the illustrations over here. So this is like a coil, it has 600 turns. And then what they're doing is that they're inserting the magnet the north pole first. And when they insert it in, right? So in this case, the magnet was stationary and the wire was cutting through the magnetic field line, right? So the wire that was moving. In this case, right, you've got the coils that are stationary, and that's connected to, again, right, the meter. And what you're doing is that you're moving the magnet. So when you move the magnet in, right, and right, either case, the magnetic field lines will be cut by the wire, right? So whether you're moving the wire or you're moving the magnet, if the wire is cutting the magnetic field lines, doesn't matter which one's moving, a current will be generated. You understand that, right?
Yes.
Right? So when they move the magnet into the coil, the field lines of the magnet are going to be cut by the coil, and that's going to, and so when they take it back out, so they can move it, they can pass it all the way through, yes, right? If that's the question that's coming to mind, they can pass it all the way through. But the point over here is the direction of movement. So even if they're passing it all the way through, the direction of movement is, one way. So from let's say this is the left side, or down to up diagonally, right? And so the current that you note when you're passing it all the way through is going to be in one direction. So the meter is going to deflect in like one way. But when you remove the magnet, you take it back out. So the direction of your movement is the opposite way. And so just like what we talked about over here, that when the direction of your movement changes, right, the way the magnetic field lines are being cut change. And so that's going to generate a current in the opposite direction. That's going to cause a reading on the opposite side. So the needle is going to go the other way, right? And so they explain that over here. right? That the magnet is pushed into the coil and it is then withdrawn. So it's taken back out. And so when it's moved in, the reading is in one direction because the current is being generated in one direction. When it's moved out, it's in the opposite direction because the current is being generated in the opposite direction, right? And there's no deflection when the magnet is at rest. So if you put the magnet inside the coil and just leave it there, you're not going to get any current. Why? Because, right, it's just there, it's not being cut. So motion is necessary, right? The movement of either the wire or the magnet is necessary for the current to be generated. You're saying, oh, well, I put the magnet inside the coils and so they're being cut constantly. And so there's going to be like a current. And so technically that's like infinite electricity. That's not how it works. Okay.
Yes.
And right, as I mentioned, the results are the same if the coil is moved instead of the magnet, right? So in the case over here where the magnet was stationary and the wire was moving, or over here where the wires are the coil, the wires are stationary, the magnet is moving. It doesn't matter which one's moving. The motion needs to be relative. One of the two need to be moving in relation to the other. Right? So if the magnet is stationary, the wires need to move. If the wires are stationary, the magnet needs to move. One of the two needs to move, and the magnetic field lines need to be cut for there to be a current. And if the direction changes, then the current flows in the opposite direction, right? If the movement changes in the other direction, the current is generated in the other direction, in the opposite direction, and so you get an AC current, right? An alternating current. Are you following?
Yes.
Okay, good. Now, right, I'm going to, because illustrations are required for this one, I'm going to, use the book. Now, what are the factors affecting the size of an induced EMF? So that is our topic, electromagnetic induction, right? So to explain electromagnetic induction, Faraday, the scientist, suggested that EMF is induced in a conductor whenever it cuts the magnetic field lines, right? When it moves across them, but not when it moves along them, right? So if it's moving in the same direction, or if it's not, cutting through them, then you're not going to get it. So the conductor needs to cut the magnetic field lines. Keep that in mind. Even if when it's at rest, it's not doing anything. So we just mentioned that. If the conductor forms part of a complete circuit, right? So in this case, right, this is a complete circuit because it's being attached and everything. Then a current is also produced. So what are the factors affecting the magnitude of an induced EMF, right? Electromotive force, or right, the voltage. Well, for EMF you don't use voltage, you use voltage for potential difference. And so you could guess, right, these are the three things: the speed of motion of the magnet or coil, whichever one is moving, right? So the faster you move it, the more EMF you're going to get. The number of turns of the coil in case of the wire, right? So the more turns there are, the more the field lines will be cut by each coil, by each turn, sorry, not coil. And so the more the field lines will be cut by each turn of the coil, right? The more current you're going to, the more EMF you're going to generate. The strength of the magnet. The stronger the magnet, the stronger the magnetic field, the more the magnetic field lines, the closer they will be, the more each turn of the coil will cut those magnetic field lines, and therefore you're going to get more EMF out of it. Okay, and so that's given over here, factors affecting the magnitude of an EMF, right? And so Faraday stated, they could ask this for 1 mark probably, right? What is Faraday's, statement about induced EMF? And so the size of the induced EMF is directly proportional to the rate at which the conductor cuts magnetic field lines, right? So the rate at which it's cutting. So what are the factors that are affecting the rate, right? Again, the speed of motion of either the magnet or the coil, the number of turns of the coil. So the more the turns, the more the cut. The stronger the magnet, right? The more the field lines, the closer the field lines, the more each turn of the coil will cut the field lines. So all of these contribute to the rate at which the conductor cuts the magnetic field lines. Okay,
Okay.
right? You need to just follow this and follow this attentively.
Yeah.
So what's the direction of the EMF, right? So the rule over here is that the direction of an induced EMF opposes the change causing it. And they explained this, right? So you've got this wire over here that's connected to a meter. And so when the wire is inserted into these coils, right, and an EMF is produced, it says that it's going to oppose the change. So what's going to happen, right, when and we know that, right, electricity has a magnetic field. So, right, sort of going like this, the magnet is, right, moving through the coil is going to cause electricity through this, and that electricity is going to have its own magnetic field. So to oppose that, when they're giving the example of the North Pole. So this is a bar magnet, and this is the North Pole. When you're moving it towards the coil, and and a current is being generated, electricity is being generated into the coil, how will it oppose the magnet coming closer, right? So the North Pole is coming closer first, and so the direction, like the current, right, the direction of the current is going to be such that a North Pole is going to develop over here, that's going to repel the North Pole of the magnet, so it's opposing the change, right? So the downward, so the induced EMF and resulting current flow should be in a direction that makes the coil behave like a magnet with its top at the north, right? The top being the North Pole. Why? Because like poles repel, and so that repulsion is, right, the opposition to the change causing it. It's opposing, so it's trying to stop the magnet from coming closer. So it's opposing that, but it is happening. Similarly, when you are moving the magnet away, now in this again, right, the direction is the same, so the North Pole, and so, right, direction has changed. You can see the needle is pointing the other way, right, and so the flow of the current is reversed. Now the coil is still going to behave like a magnet, but in this case now the top part is going to behave like the South Pole. Why? Because the magnet is moving away, and how do you oppose the movement of the magnet going away from you? You're going to try and attract it, right? And to attract it, you need the South Pole. Okay,
Okay. Yeah.
so again, that is given over here. Now, they mention that this behavior is an example of the principle of conservation of energy, which we talked about way back in Unit 1, right? That energy is neither created nor destroyed, but it is converted from one store to the other, right? And it is conserved, right? So the total energy of the system remains same. And so how does it work? If the current produced by a magnetic field of opposite polarity to those shown in each coil, electrical energy would be created from nothing, right? And so that would mean that, right, when you're bringing it close, this is going to be the South Pole is going to attract it. And so in terms of how this is working, they're saying that, right, electricity will be produced from nothing, which electric energy is produced from nothing, which can't happen,
Yes.
right? And so how is this conservation of energy, right? Why? Because work is done by whoever moves the magnet to overcome the forces that arise. So when I'm moving this through and there's a repulsion, I need to push it through. And so the work I'm doing on the magnet to overcome the repulsion and push it through the coil, that is being converted into electrical energy. Similarly, when I'm pulling it out and it's being attracted, and so I need to overcome that attraction and pull it out. So I'm doing work to remove the magnet, and so that work is being converted into electrical energy. So that's how the conservation energy works in this case. Did you follow that?
Yes.
Not very confident.
I mean, it's a yes. I understood. I'll have to reread it.
Yeah,
Maybe more.
definitely. Okay, now here we come to the first rule. Right, so for a straight wire moving at right angles to a magnetic field, because whatever motion we've seen so far, right, this is the coil, this is the magnetic field, and so, right, again, whether you're moving the magnet or you are moving the wire, right, the field lines are going from north to south and the wire is moving up and down, right, so it's at right angles. Similarly over here, right, the field line is sort of within the plane of the page, right? It's going north to south in both cases, and so it's sort of, let's say, horizontal, and the coils over here, right, these sides are vertical, and so they're at right angles, and so they'll cut the magnetic field. So for a straight wire moving at right angles to a magnetic field, the direction of the induced current can be found by Fleming's right hand rule. Right, now they're given the illustration over here, and so it's also called the dynamo rule. So what they're doing is hold the thumb and the first two fingers of the right hand at right angles. By the way, this is part of your IGCSE, even though like extended, but yes, it's part of your IGCSE. For the O level, Fleming's right hand rule is not part of the syllabus, right? It's given in the text, but it's a going further thing.
Okay.
Right. So, right, does the illustration make sense of how you need to hold out your fingers?
Yes.
Are you sure?
Yeah.
Okay, you need to hold them out like this. Let
Wait.
me.
Okay. We just have to stretch it out like in the image, right?
But how do I, prioritize my window? Oh, no, not always. Come on, stop. What are you doing? Okay, I don't know what's happening over here. I haven't done this. This is how you do it, right? So this is what it looks like.
Yeah. Yeah.
Okay, so all of these are at right angles to each other. Okay,
Yeah.
so what they're saying is, right, you hold your hand like this. Let
Like
me,
a gun type.
yeah, kind of, right? So thumb, finger in this case pointing towards you, and the second finger, right, in this case because I'm pointing towards you, so it's going towards the left. Okay,
Yeah.
so
Yeah.
that's how you hold it. And so, right, the thumb, right, the first finger represents the field, right, the direction of the field, magnetic field. The thumb is the direction of motion, and the second finger is the direction of the induced current. So if you want to figure out, oh, which direction is the induced current going to be, and so over here in the definition, right, when the thumb and the first two fingers of the right hand are held at right angles to each other with the first finger pointing in the direction of the magnetic field, and the thumb in the direction of the motion of the wire. And they say over here the direction of the motion represents the direction in which the force acts on the conductor.
Oh, okay.
Then the second finger points in the direction of the induced current. So this is going to help you figure out, right, which way the current is going.
Could you repeat that?
I can. Okay, so here is a video I just pulled up. Right, let's see how they're explaining this. The title is how to use Fleming's right-hand rule to work out direction of current. So hopefully they do what they're saying.
These conductors. So here we've got a conductor that is being passed through a magnetic field, and it's going to be passing in this direction. So that conductor, which we've got a cross section of there, is passing through the magnetic field in a downwards direction. So let's get our hands in position. So here is the way that we hold our hands for Fleming's right-hand rule. You can see there you sort of make that kind of J shape with your finger and your thumb there, and then your second finger sticks out at a right angle. So each finger is at a right angle to all the others. So we know that the lines of magnetic flux go from north to south, and we've got our first finger flux or first finger field. So that's going to go from north to south in that direction. And then your thumb is the movement of the conductor. And in this case, the conductor is moving downwards like that. So the conductor is going to move down, okay? And what that means is that my second finger, which represents the current flowing through the circuit, is going to be going into the board away from us. And if you'll remember from a previous video in our series on magnets and magnetism, you'll know that that represents a cross like that indicates that the current is going away from us, much like the flight of a dart. If you throw a dart away from yourself, you'll see the flight going away like that.
Just to clarify, the cross that he just made is not like the positive terminal. Okay, it's just to sort of indicate that the current is flowing away from you into the screen. Okay.
Okay.
So let's have a little look at what happens now when we reverse the magnetic field. So here now, we've got lines of magnetic flux going from north to south in this direction. We'll still say that we are moving the conductor downwards. So the conductor is going to be moving in a downwards fashion. And that means now I need to move around, because here I need to point from north to south with my forefinger. So knuckle at the north pole, pointing towards the south pole. My thumb indicates the direction of movement of the conductor, which is going to be going down that way. And then our second finger represents the current flow, which is coming towards us. So we represent that with a little dot inside the conductor there. So you can see that by changing the direction of the magnetic field around, we've changed the direction of the current flow. What do you think is going to happen when we change the direction of the motion of the conductors? Well, we'll have a look at that next. So you can see here, we've reset the board. We've now got our magnetic fields as they were. And what we're going to change this time is we're going to move the conductors upwards like that. So again, we've got lines of magnetic flux will be going from north to south. So I need to stand over this side and point from north to south with my knuckle at the north pole. My thumb indicates the direction of movement or motion of the conductor. They've both got the M sound in there. And then the current, represented by our second finger, is going to be coming towards us in this case. So you'll remember from a moment ago that this had a dot, had a cross in it a moment ago, and now we're going to put a dot in there to indicate the current flowing towards us out of the board. So there you go. We've got there, having changed the motion of the conductor, we've changed the direction of the current flow through that conductor. Let's have a look now at what happens when we move the bottom conductor upwards like that. So again, if I stand over this side, you can see we've got lines of magnetic flux going from north to south. So my first finger flux or first finger field, all starting with an F. I put my knuckle at the north and I point to the south pole, and then my thumb indicates the direction of motion or movement of the conductor. And therefore my second finger is pointing into the board, which means that the current must be going away from us in that direction. And that's what we've got going on there, and you'll see how that corresponds to what we looked at earlier on when we had the magnet and the galvanometer out on the table. So hopefully from this video, we've seen that Fleming's right-hand rule helps us to figure out which way the current is going to flow in a conductor when we pass it through a magnetic field. This will help us to understand a little bit better how generators work and things like that. And also hopefully we'll have a much better understanding of these type of questions for when we take our exams. So all that remains in this video.
Right. Hopefully that helped.
Yeah.
Right. Much better explanation than what's given in the book. Okay.
Yep.
In fact, I'll share the link for this. In like, do we have time? We have a few minutes, right? If I just go
Video
back
is to say,
earlier, he's going to demonstrate.
that's going to be very important.
Right? You can see when he moves the wire, the needle going in the opposite direction. So let's do that as well.
For understanding Fleming's right-hand rule. And our galvanometer, previously we watched the needle deflect on the video, but what we're going to do on this video is we're going to have a look in a little bit more detail about how exactly that's behaving. So if current flows in that direction through the meter, the galvanometer will deflect that way. If the current flows in this direction, exactly what Fleming's right-hand rule, do it as in the classroom. The magnetic, which has the muck, think about it. So on our magnet, we point to the south field, so it is correct. Now, if I take my conductor and I pass it through the magnetic field, have a look at which way the needle deflects. Let's have a look. So if we pass the conductor through the magnetic field, watch the needle carefully because it won't deflect an awfully long way. So did you see there the needle just went that way, just a little bit, so it deflected in that direction. Now does that apply or comply with what we said about Fleming's right-hand rule? We've got the direction of the magnetic field north to south, we moved our conductor in a downwards direction, so my thumb is pointing downwards, and then the current should have flown in this direction down the conductor, so it flew this way through the galvanometer in that direction, which is why the needle deflected that way. So you can see there that Fleming's right-hand rule actually works. We can now just prove it in the other direction. So now if I move my conductor up through the magnetic field, I've still got the north pole, knuckle north pointing to the south, but this time I'm going to move the conductor upwards. So my thumb for the movement of the conductor points upwards, which means that the current will flow in this direction through the conductor. So again, let's see if that's correct. Watch the needle carefully. So again, we might have seen that deflect just ever such a little bit in that direction, which means that the current is flowing this way through the galvanometer. So therefore, Fleming's right-hand rule holds true. Now, of course, we could also change the magnetic field around and we would find that that would affect the way that we hold our hand. But what we've proved here is that Fleming's right-hand rule works. Now, this has been fantastic from an experimental point of view. However, we also want to make sure that we're able to answer our exam questions correctly when we come to do our electrical exams.
Okay, and I believe that's going to further clarify Fleming's right-hand rule that we just covered.
Yes.
Right. So if explained properly, it's not that challenging. Okay. So
Yes.
I'll stop here and we'll continue next time, and I'll carry this forward the other rules. So we'll try and see how the book takes them, how well I can tell that to you, and we'll obviously take help from videos to further our understanding. All right, so I'll see you guys next time, inshallah.
Okay. Allah Hafiz.